This part is momentum transport by convective force. This part is momentum transport by molecular force. So our work should be associated with which part? This part or this part? If you look into open system energy balance, I told you that in open system energy balance, you have change in energy with respect to time equal to energy in minus energy out plus Q plus work. Work here is divided into two terms, shaft work and PV work, which is flow work. You take energy here from kinetic potential internal. Internal here and flow work here combine to get enthalpy, right? So the work that is considered flow work is essentially PV. So P here resides in this term. So we will look into pi instead, not convective form. Okay? The unit of pi here is supposed to be Newton per square meter. Same unit as shear stress, a force per area. This amount can be considered as force acting upon the area. That force pushes fluid to move from one point to another. So that force would act for the work. Okay? So now we are going to replace that to get pi. Let's look into each direction. If you have x, y, and z, and this is the area, pi x supposed to be force in x direction acting on the area perpendicular to x direction. So pi x goes in this direction. Okay? So if I calculated force according to pi x, I'm going to have pi x, which is vector in this case, dotted by velocity to get work. Right? This work is supposed to be work per unit area, because now pi is Newton per square meter. But in this formula, F here is Newton. So if I replace pi to force here, you will have Newton per square meter. So the unit of everything here is supposed to be Newton per, Joule per square meter second. Right? So this would be rate of work applied in x direction, or applied according to the flow in x direction per unit area, per unit time. So then you are going to have pi y and pi z as well for work in x, y, and z direction respectively. If you combine them, you get pi as a tensor in all three directions, dotted by velocity. This would be rate of work by flow work in all directions. Okay? You might get a little bit confused because here, pi here is a tensor. It has 9 components. Okay? But I write down here as pi x as a vector. Now it has 3 components. Pi is supposed to have 2 subscripts, just like phi or tau. So you have pi xx, pi yx, pi zx, and so on, right? Again, if you take pi here as the meanings of force per unit area, the subscript on the last subscript supposed to give you direction of the force. The first subscript is direction of the area perpendicular to it. So if you take pi x, that means all force acting in x direction. I'm going to write it down as pi x. So this is reduced from 9 components to 3 components. This pi x is dotted with velocity in x direction. According to that, the formula, force dotted with the velocity. That worked. But doesn't matter. So you have pi x, pi y, and pi z. All 3 equations should give you 9 components back. And then you recombine 9 components again, you get this relationship. Okay? So this pi tensor dotted with velocity should represent work act on the system by flow work. Okay? So now we have derived Q, which is conductive energy flux. We have convective energy flux. And we have work from flow work. All right? These 3 terms combined is called combined energy flux, E. All right? Conduction, convection, work. But pi itself is pressure term multiplied by, added by shear stress tau. So that means pi dot V should equal to pressure times velocity plus tau dot V. You have tensor dot by vector. The result should be a vector. Okay? Everything else is vector. So I'm going to have PV here. And everything here, these 2 terms, would have V multiplied by it. So I'm going to group them together. So that's Q. These 2 terms, if I take density out, inside there will be specific internal energy plus pressure over density, right? One over density, you should get specific pressure, a specific volume. 1 over density is specific volume. So you have U plus PV. The whole thing here turns to be enthalpy. So as a result, you get combined flux equal to Q plus 1 over 2 rho V squared plus rho H V plus tau dot V. This will be combined flux that we are going to use in shell balance. Remember, in shell momentum balance, we use phi, right? We take phi in and out from a shell and then take a balance. Same thing would apply for energy shell balance, but we use E instead. So E is consisting of 3 terms. All right, any question? Did I go too fast? So in general, just review of today's class, we start talking about similarity between momentum and energy transport, and then define molecular transport for energy term, which is represented by Fourier law. Then we define convective term, just look into energy of the fluid flow through a part of the area. By that definition, we can derive convective energy transport. Lastly, we derive work, because energy can be transferred in terms of work. And work in the system that the fluid flows can be derived from force dotted velocity, and you get this term. These 3 terms combined, you get combined flux or combined energy flux. But with some manipulation, you can change internal energy into enthalpy. We prefer enthalpy because mostly our system is constant pressure, it's not constant volume. We can calculate enthalpy from heat capacity at constant pressure. All right, so we finished chapter 9. We're done with chapter 9. Next week, I'm going to start shell balance, shell energy balance, and give you several examples. Okay? Also, handout will be given next week.